we're going to see when certain elements of a transfer function can be neglected, thereby allowing us to approximate it by a simpler function, one with reduced order and consisting only in some of the terms in the original transfer function. So, for example, in this function here, maybe a good approximation could be given by, I don't know, just k over one of the poles. Maybe s over p2 plus 1. This could be a good approximation of the original transfer function if certain requirements hold. And well, we're going to see what those requirements are. So as we saw in the last video, this is the crudest, the most unsophisticated way or approach to order reduction, yet one which is very useful. Now, there are two mechanisms that allow us to disregard first or second order elements, in this case this one and this one and this one, in a transfer function, which are dominance and cancellation. So let's go first with dominance. Well, we've already come across dominance when we studied second order systems in which the damping factor were a lot greater than 1. In that case, we saw that the poles were very far away from each other, and in this case the system could be approached by just the closest to the origin. And in that case, we said that this pole was dominant. Also, when we studied the effect of zeros, we saw that zeros very far away had no effect on the step response of the system. So the general rule is that what determines the relative importance of an element is what determines its contribution is its closeness or its proximity to the origin. And therefore, the dominant poles of a system are those those closest to the origin. For example, in this system here, this minus p would be the dominant pole, and maybe this second pole minus p2, this is p1, would be dominated by p1. But the question is, can we disregard P2? Can we approximate the behavior of this system just by one of first order, including only P1? Well, the criterion we'll use is that given by a semicircle in which the radius is several times the distance from the origin to the dominant pole. In our case, 5 times. Although you could use 4 or 6. It depends on well, in what you prefer. So maybe this would be 4 and 5, and we can draw this semicircle, and P2 would be out of it. And therefore we could disregard P2 and approximate the system just by one of first order with minus P as its pole. In a more general setting, I don't know, maybe we could have these two poles, maybe here another pole and a 0 here, and also, I don't know, maybe a couple of poles here and a couple of zeros here. Well, if we draw the same semicircle, this would be the radius. Well, we had to go 5 times far, and this could be our semicircle. Now, in the approximation, in the reduced order approximation, we would have to keep the two dominant poles, but also this 0 and this pole, but we could disregard these others. We could not consider them. We don't care about those. So we would get a third order reduced transfer function. Now it is very important to remember that only the dynamic part of the elements must be disregarded and not the gain. So for example, in this system here, g of s is equal to s plus 2 over, I don't know, s squared plus 2s plus 3 times s plus 100. Okay, well, I don't know, maybe I should multiply this by 200. So we see that there's a pole which is very far away from the others, and maybe we could say, okay, let's approximate this by all the terms but s plus 100. S plus 100, s squared plus 2s plus 3, and we get rid of this s plus 100. Well, this G reduced order of S has a different gain than that of the original system, and that's a mistake. That's a terrible mistake, because G of 0 was equal to 400 over 600, which is 2/3, but GR of 0 is equal just to 400 over 3. So not only we've got rid of the pole, but we've also changed the gain of the system, and that's something which is not allowed by dominance. One of the requirements of reducing order or the order of a transfer function is to keep the same gain. So we must always check that this doesn't happen. And one way to do it is by using always the standard notation. We could have written the previous transfer function as s over 2 plus 1, and this would be 200 times 2, and this over s squared over 3 plus 2/3 of s plus 1, and then we had to divide this by 3, and also s over 100 plus 1, so this is 3 times 100. And now we can disregard this term, because this term has unit gain, and we can apply dominance without any threat of changing the overall gain of the system. Now, regarding cancellation, we've also come across cancellation in previous videos. Cancellation. We saw that when a pole is very close to a 0, its residue tends to be very small, and its contribution in the overall response vanishes. So if we have a couple of poles and maybe a third pole here, well, when a zero is very close, no, this was a pole, a pole. So when a 0 is very close to that pole, the residue associated to this pole tends to 0, and the system then can be approached by just these two elements, or by one with only these two elements. Now this cancellation could have happened also here, but in that case the 0, this is the pole and this is the 0, the 0 would have had to be closer to the pole. In order for a 0 to cancel a pole which would otherwise have dominated, it has to be really close. So for example, in the case if we are out of the sphere of, or the ball of dominance, we don't really need to cancel it, because we are actually disregarding it without the need of a zero at all. If once we are inside the dominance radius, well, you have to have a zero close to the pole in order to cancel it. But as you get closer and closer to the origin, the pair has to be closer and closer. They have to be almost in the same position, because otherwise we cannot disregard their contribution. And now let me finish with a very big warning, which is: do not ever cancel elements in the right half plane or the imaginary axis. You cannot cancel poles. You cannot cancel this pole or these two poles. And the reason for that is that you never really get to know the exact position of a pole or a zero in a system. There's always certain amount of uncertainty in the model, and it is impossible to match the exact position of the pole with a zero. You cannot put a zero exactly over your pole. And if the pole is unstable, well, look what happens. Here is an example. If g of s is equal to s over 1, well, let's begin with the poles. We have a stable pole s over 2 plus 1. This is minus 2, and also there's another pole in s over 1 minus 1, which means that we have a pole here at 1, which is an unstable pole, a right half plane pole. If we want to cancel it by using a zero, well, we introduce a zero in the system, s over 1 minus 1. And that's fine, because this is equal to 1 over s over 2 plus 1, with a step response, for example, like this. Very well. But the problem is this pole really here? What happens if, I don't know, the system changes, or maybe the temperature affects the system, or it becomes worn out, and I don't know, maybe this can be 1.001, just a slight change, just a very tiny change. But the consequence is that when we calculate the step response or any other response, well, as we know, we have some residue over s plus some other residue over s plus 2 plus some other residue over s minus 1.001. And unless the zero is exactly over 1.001, this is going to be different from 0. And the zero we introduced was in 1, so now R3 is different from 0, which means that there's some contribution, there's some positive exponential here, which is e to the 1.001 t. And this term with a tiny 0.00, I don't know, 0.0007, for example, I don't know, I haven't done the calculations, but this will eventually grow. This term will eventually, as time goes by, it will grow, and the overall response will become unstable. This will eventually be the dominating part, and the system is unstable, despite the fact that we've tried to cancel the unstable part with a zero. So do not ever cancel poles or zeros in the right half plane or in the imaginary axis, only in the left half plane. And again, when you perform cancellation, try to do it always in the standard notation, or at least check that after your operations you get the same steady state gain.